Bom, vamos começar a nossa sessão de sistemas dinâmicos. E o primeiro palestrante do dia e da sessão é o Edson. O Edson vai falar sobre o trabalho dele, um pouco sobre creio, Wellington. E, bom, o Edson está avisando que, como ele é paulista, ele vai precisar falar inglês para poder ser entendido. Tá? Então...
Ok, vocês estão me ouvindo? Dá para ouvir ou não? Está um pouco baixo? Não. Ok, well, I've been told that there is at least one person in the room that doesn't speak Portuguese, so I will speak in English, and besides the slides I prepared in English anyway, so. Okay, so this is based on joint work with Trevor Clark and Sebastian Van Strien from Imperial College. This is meant as, I would say, a tribute to Wellington de Mello, who unfortunately passed away last December. I had a long collaboration with Wellington over a period of about 15 years. We didn't write many papers. We wrote like 3 long papers, but we wrote also 2 books, okay? And I can just really, in a few words, just describe what it was to have the chance to work with Wellington. It was quite an honor. I think I learned a great deal. You know, he was, to me, more than a collaborator. He was a mentor and a friend, okay? I think that one of the things that I appreciated the most working with Wellington was his intellectual honesty and his sincerity. He was an extremely honest person, extremely sincere. Sometimes he was brutally sincere. You know, he could make you feel a little bit, you know, maybe low on yourself. But it was always meant in a good way. It was always meant in the sense of sort of advancing math. Okay. So, I mean, he taught me many things, and I think that, you know, he would have, I think that he would have appreciated this work. I had the chance to mention to him last year that we had started doing this, but most of the results are actually, you know, they were obtained in the last few months. So, you know, I didn't have the chance to tell him that, okay? So, first of all, the underlying theme of this talk is renormalization of one-dimensional dynamical systems, and more specifically, renormalization of unimodal maps. So let me just remind you that a unimodal map is a map of the interval, something like this, which has a unique critical point. The critical point in this talk will be given by an even criticality, so it could be like a quadratic or quartic or sextic critical point. The maps will be smooth, at least C3 smooth, okay, for the most part. And before I go on, I will try to describe to you what renormalization means, even though this was already mentioned in Arthur's talk last night or last afternoon. So before anything, you know, I start anything, I want to sort of get something out of my system, okay? Which is this formula that you see here on the right. So a lot of people working in one-dimensional dynamics, I mean, almost everyone working in one-dimensional dynamics is familiar with something called the nonlinearity of a one-dimensional map, and in particular is, you know, familiar with the chain rule for the nonlinearity, okay? Now, not everyone is familiar with the fact that when you go to higher dimensions, you have something which is sort of like that, which is the chain rule for the second derivative, okay? So here, F and G are maps in Rn, and they are both C2, and if you try to calculate the second derivative of the composition of these 2 maps, you get a formula like that where, where there appears this funny tensor product here, okay? So this is, you know, the second derivative is like an n by n square matrix. It consists of the juxtapositions of the n Hessians of the components of the map. So this is an n by n square matrix This is an n by n square matrix. The tensor product is an n square by n square matrix, so it makes perfect sense to multiply these two matrices. And similarly, this is an n by n matrix, and this is an n by n square matrix, so the result is an n by n square matrix. So I haven't seen anyone use this formula in papers in higher dimensional dynamics, okay? So in the work that I'm going to talk about, even though I'm not going to show you how, this formula intervenes in a very essential way, okay? So if you don't get anything out of the talk, if everything becomes a bit complicated in a while, forget everything I'm saying. Just remember this formula. Go home, work it out, and try to make some use out of it, okay? We employ this formula for the second derivative of iterates of a certain map, okay? So, and it's really important, the shape of the formula. Anyway, I'm not going to get to that because I only have 40 minutes, and I already spent maybe 6 or 7 minutes. So, so what is renormalization? So yesterday, Artur more or less told you what renormalization was. You have a unimodal map. You compose the unimodal map with itself a certain number of times. You restrict to a certain interval, and then you linearly rescale that to unit size again, and you get a new unimodal map. Okay, so that's an operator. So, formally, I can define it like this. The unimodal maps that they're going to be normalized to be defined on the interval -1, 1. They will all be symmetric with respect to 0. 0 will be the critical point. And being renormalizable means that you can find a symmetric interval around 0 such that after a certain number of times, this interval returns to itself, and the restriction is, again, a unimodal map. Okay? So you can define the renormalization in this fashion. You just take this iterate, restrict it to this interval, and you linearly rescale by this factor lambda, which is just given by the pth image of the critical point. You get this new map, RF, and this new map is also unimodal. Okay, so in fact, if you look at the interval that goes from minus lambda to lambda, and you look at its images up to time p minus 1, you get a sequence of disjoint, pairwise disjoint intervals. And these are permuted by f. So just to give you I'll give you a picture in a minute, but let me just say that it may happen that the renormalized map is itself renormalizable, in which case you can calculate the renormalization of the renormalization, so you get the second renormalization of f, and so on inductively for as long as you can. In particular, we're interested in maps which are infinitely renormalizable. You can renormalize them as many times as you want. Okay? So here's the picture. So here's the interval -1, 1. And you have to imagine that there's a map acting there, which is unimodal. Being renormalizable means that you can find a sequence, finitely many intervals, which are pairwise disjoint, in this case 4 intervals, one of them containing the critical point, symmetric about the critical point. And then what the map does is it takes the interval containing the critical point to an interval containing the critical value here at this rightmost point. Then it takes that interval to another interval, which is the leftmost one. Then it takes that one to another interval, and so on until you come back. Okay? When you come back, you look at this return map. In this case, p is equal to 4 in this picture. You linearly rescale everything by this factor lambda, and the new map, the renormalized map, acts on this rescaled picture. Okay? So this is what renormalization means. It's like zooming in near the critical point and blowing it up. Okay? So you want to examine the dynamics. Microscopically, you want to examine the dynamics of the map. You use this microscope, which is renormalization. Now, before I go on, I have to tell you just a little bit of history. So the theory of renormalization of one-dimensional dynamics, it starts with some very important and really incredible empirical discoveries by these pairs of, these two sets of physicists, Coulomb, Tresser in France, Feigenbaum in the United States. They both, all three of them, they worked independently. They published 2 papers in the Journal of Statistical Physics in the same year about the same thing, okay? And what was the discovery? The discovery was that if you look at one-parameter families of unimodal maps like this, going from a situation where you have no dynamics like this, very trivial dynamics where you just have a fixed point, to all the way when you get full dynamics, when you get something that looks like a von Neumann map or something. So an example of such a family would be the quadratic family, except that here I'm considering the map in the interval 0, 1 rather than the interval -1, 1. Lambda here is a parameter that varies from 0 to 4. And as you increase the parameter, the dynamics becomes more complicated. And in particular, there's first a moment where the critical point is fixed. Then later on, the critical point becomes periodic of period 2. Then further on, it becomes periodic of period 4, and so forth. So you have the sequence of period doubling bifurcations. And what Feigenbaum and Coulant-Tresser observed is that if you record the values of the parameters for which you have for which the critical point is periodic of period 2 to the n, then if you look at these ratios between successive differences of these parameters, this converges to some number, okay, which is universal. It does not depend on the family that you're considering. This was really fantastic, okay? And moreover, at the end of this cascade of period doubling bifurcations, you have a map which is if you call this f sub lambda, you have f sub lambda sub n, so you have the lambda sub n's converging to some lambda infinity, and you have this map f sub lambda sub infinity, okay? This map, turns out, has the property that the critical point now is no longer periodic. It accumulates on a certain Cantor set, and what they discovered is that the geometry, the asymptotic geometry of this Cantor set was universal. All the ratios that you have become like universal numbers as you go down and further down the scale, okay? So this was a beautiful discovery, but they not only discovered that, but they also proposed an explanation. The explanation is that there was this renormalization operator that I just defined to you, except that in their case it was just period doubling. So it meant that every time you renormalize, you only have like 2 intervals, which are permuted by the map, one containing the critical point, the other containing the critical value, okay? So the proposed explanation was that this operator had a fixed point, okay? That this fixed point was hyperbolic in some sense, in some space of maps, and that all the features, all the numbers that you extracted, like this number here, they were eigenvalues of this operator, of the derivative of this operator at the fixed point, okay? So this was the proposed explanation. And it didn't take long for a guy called Lanford, Oscar Lanford, to give a computer-assisted proof of this conjecture in a very special setting. He looked at certain real analytic maps. He wrote them like power series, and he put some norm on the coefficients of this power series. So it became something which was part of a Banach space. And in this Banach space, he was able to show that the renormalization operator was analytic, number one, and that indeed it had a fixed point, and that this fixed point was hyperbolic. But everything was done numerically, but with rigorous numerics. Okay, it was a rigorous proof, but it used like interval arithmetic, all sorts of, a numerical analysis. Okay, so it's kind of a tour de force in some sense. It at least shows you that the conjectural picture is true, but it's not conceptual. It doesn't tell you why things are true. In math, you also want to understand why things are true, not just that they are true, right? More or less around the same time, Campanino and Epstein, they were aware of what Lanford was doing, and they, looking at Lanford's work, but working independently, they proved the existence of this fixed point of renormalization by using something like Schauder's theorem. So it was just the existence of fixed point, non-constructive, just shows the fixed point exists, doesn't show anything about hyperbolicity, okay? And I say here without essential help from computers, because there was a secret moment in the paper where they needed to know that they needed to use some inequality, and the only reason they knew the inequality was true is because they had done some calculations with a computer, okay? So the proof actually depended on a computer also. So there was this challenge of trying to understand conceptually what was happening. But before this was done, let me fast forward like 15 years or 14 years. There is this guy, Davy, who's an analyst, a very, very strong analyst. He was able to take Lanford's work. So he assumed Lanford's hyperbolicity result, which was for a space of unimodal maps that was like real analytic. All the maps were real analytic. And he pushed this hyperbolicity through a larger world of C2 plus epsilon maps, okay? Of unimodal maps which are just like C2 plus epsilon. So this was a tour de force, but it used Lanford's computer-assisted result, okay? More or less in between, 1982 and 1996, in the late 80s or something, Lanford realized, Lanford and others, and when I say others, I mean people like Rand, Setna, Siege, and so on, they realized that the period doubling situation was actually a special case of this renormalization operator that I defined here in the beginning, where you don't necessarily have to have period doubling. You can have like period tripling, or you can have combinations of these things. You renormalize once, there's like period 2, then you renormalize a second time, there's maybe period 5, and you keep doing that. So in the end, what the conjectural picture that emerged was this one. I'm giving a kind of a loose statement, informal statement. So the idea would be that there is this renormalization operator acting on the space of unimodal maps, on some space of unimodal maps, and that this operator actually had, behaved like an infinite dimensional horseshoe. There would be a limit set, which will be a hyperbolic Cantor set, okay? So at every point of this Cantor set, every point meaning a map, right? You would have like a hyperbolic picture with a one-dimensional unstable manifold and a codimension one stable manifold everywhere. I didn't say that over there, but that's very important, okay? So this was the conjectural picture, and he was also working in the situation where we have bounded combinatorial type. What does that mean? That means that when you renormalize, a map has bounded combinatorial type if it's infinitely renormalizable, and every time you renormalize, the number of intervals that you see in the definition of the renormalization is bounded, okay? So for instance, period doubling is bounded because it's always 2, 2, 2, 2, 2, okay? But there may be also unbounded situations. I'll mention that in a moment. So the challenge was to find a conceptual proof of this conjecture. And the first major breakthrough was given by the work of Sullivan. 1992 is really the date of the publication, but Sullivan was working on this for at least 7 years, maybe more. And he was able to tie the subject of studying renormalization of one-dimensional maps to the study of quadratic-like maps. So let me just tell you briefly what a quadratic-like map is. So it's a holomorphic map, which is defined on some disk, some topological disk U, and maps this topological disk U onto a larger topological disk V. Okay? So it's holomorphic. It's a proper branch covering map, branched at a unique critical point. So there's a critical point here. And the map is, except for this critical point, the map is a nice covering map. Okay? And it's holomorphic. So what does this have to do with that? So what Sullivan observed is that if you start with something, say, which is real analytic, a unimodal map which is real analytic, and you start renormalizing it, if it's infinitely renormalizable, you start renormalizing after a sufficiently large number of iterates of renormalization, you reach a situation where you have a real analytic unimodal map that has a nice complex extension, okay, a nice holomorphic extension to the complex plane, to a neighborhood of the interval in the complex plane, which looks like a topological disk, and maps this topological disk out onto a larger disk, just like that. Okay? So it's sort of inescapable. You reach the world of quadratic-like maps. Okay? And moreover, I mean, I'll give a formal statement of Sullivan's theorem in a moment, but he actually showed that even if you start with something which is not real analytic, then if it's just C3, say, and you start renormalizing it, asymptotically you'll go to this world of quadratic-like maps. Okay? Quadratic, when I say quadratic, is because I'm thinking of the critical point as a quadratic critical point, which was the situation originally examined by Sullivan. Okay? But this is later generalizable to arbitrary criticalities, even criticalities. Okay. But he was able to actually show that this infinite dimensional attractor existed. He showed the existence of the attractor, and he also showed that it was indeed an attractor in the sense that as you renormalize, things converge to this Cantor set. but he was not able to show that the convergence was taken at an exponential rate. Okay? So this was done later by McMullen. It's a very beautiful, all of these are very beautiful theories, but this one by McMullen was part of the reason, or the main reason why he won the Fields Medal in 1998. Okay? But then the real, final breakthrough, in some sense, or almost final, was given by Lyubich. He was able to, forget about the problem for the unimodal maps. Just think about these quadratic-like maps and work with renormalization of those maps. These maps can be renormalized in some sense, which I'm not going to describe here. But working in this setting, he was able to show that the renormalization operator was hyperbolic. If you think about it for a moment, these maps, they don't have they're not canonically defined. It's the same holomorphic map can be quadratic-like for different pairs of disks. Okay? So the correct thing to do is, instead of working with the maps themselves, is to work with germs of quadratic-like maps around their so-called Julia sets. So this is another thing I should define here very briefly. When you have a quadratic-like map, there is something called the filled-in Julia set. So you can define a compact set, which is just take this larger disk and start taking pre-images of this disk by F. So you take the intersection of the pre-images of V by F. Okay? So we've got a compact set which is totally invariant. This is called the filled-in Julia set. And the boundary of this set is called the Julia set. Okay? So JF is the Julia set, KF is the filled-in Julia set. And what Lyubich did was he worked on, on germs of maps like this around their filled-in Julia sets. Okay? So the whole, incredibly clever thing he did was he found a differentiable structure in the space of all such germs. Okay? He modeled this space of such germs as a manifold on a topological vector space that was not Banachable. Okay, so it's a very intricate thing. So, again, it's truly deserving of a Fields Medal as well, but, I don't know. So, but then later on, this theory was, put in sort of essentially final form, the theory of renormalization of quadratic-like maps or polynomial-like maps by Avila and Lyubich. What they did is, first of all, they got rid of this obstruction of working only with quadratic critical points. So they took care of all critical points, all types of critical points, quartics, sextics, and so on. And they also got rid of this bounded type hypothesis. So now you could deal with renormalizations of things that the periods could grow, right? You could have period 2, period 5, and then all of a sudden maybe period 1 million, and then period 1 billion, and so on. Okay? So they showed that there was this larger attractor now. So it's now an infinite dimensional horseshoe, but it's modeled on a shift on infinitely many symbols rather than finitely many symbols. Okay? This is a very beautiful piece of work. I think that the main paper is actually published in Publication Mathématique de l'IAGS, if I'm not mistaken. And it was really kind of a final word as far as the holomorphic theory was concerned. Okay? Now, before this result and after Lyubich's result, in between these two, in 2006, Wellington de Mello, Alberto Pinto, and I, we examined the case of finite differentiability. Okay? I think that Artur mentioned this yesterday in his talk. This became very, very, very technical. But it was closer in spirit to what the Lanford's conjecture was all about, because Lanford's conjecture was really about unimodal maps, not quadratic-like germs or things like that. So what we did is we took Lyubich's theorem, which was giving this hyperbolicity of renormalization in this very abstract setting of quadratic-like germs, and we transported that back to the interval by combining that with this method of Davy. You see, Davy took the hyperbolicity of Lanford's theorem, which was for certain spaces of real analytic maps, and he pushed that to the space of C2 plus epsilon maps. What we did is similar to what David did, except that David did that to something that was related only to period doubling. So it was just one point in this attractor, whereas we do that for the whole attractor. Okay? So there's a lot of hard analysis involved in this. One of the major technical difficulties here is the fact that the renormalization operator in the CR sense is not Fréchet differentiable. Because, and I think that Arthur mentioned this yesterday also, en passant, composition, which is involved in renormalization, you compose a map with itself a certain number of times, composition is a very ill-behaved operation with respect to differentiability. It's not differentiable at all. It's just continuous. Okay? It's not even Holder continuous, just continuous. So there is even a technical difficulty defining what it means for an operator like that to be hyperbolic. But it is possible. And we not only do that, but we construct the stable manifolds. We construct the unstable manifolds and so on. Okay? And we prove that there is a hyperbolic structure for the attractor. So this is like 100 pages of it's really almost 100 pages of hard estimates and things like that. So it took a long time to do it. And we went a little bit beyond the conjecture. We also proved something about the stable manifolds. We showed that they form a lamination that has a certain transversal structure, a certain holonomy, which is C1 plus beta for some beta. Okay? And this was just in the bounded type case. So presumably, one can take Avila and Lyubich and jack it up and do the same thing we did here and cover all unbounded type cases. Okay? I have never had the energy to do that. So this proof is okay. It's fairly complete. It has even some low differentiability assumptions. The differentiability has to be just a little bit less than C3 is already enough. Okay. However, the proof is, like I said, long technical, and to be quite frank, when I look at it, I say it's ugly, right? So I don't know what someone may remember here. Who's the mathematician who said that there is no permanent place for ugliness in mathematics? But what is it? It's beauty is the first test. There's no permanent place for ugliness in mathematics. Who said that? Hardy. Yes, Hardy. Godfrey Hardy. Good. So thinking about that, we started to say, well, so the motivation for my work with Sebastian and Trevor is the following. Is there a way of unifying the beautiful theory in the holomorphic case, the theory by Sullivan, McMullen, Lyubich, Avila, with this sort of ugliness of the CR world? Is there a way of, finding some method that more or less does all these things at the same time? So the key is to think about this picture. So rather than thinking of polynomial-like maps like the ones I defined, which are holomorphic, we'll generalize this notion to maps which are no longer holomorphic, look like this. They look like they are branch coverings, like that, but they're not holomorphic. They are just CR, but they have a special feature of being asymptotically conformal as you get closer and closer to the real axis. Okay? So the idea is to use this notion that I will define in a moment of asymptotically conformal analogs of polynomial-like maps. Okay, the idea of using asymptotically conformal dynamics itself is not new. Okay? In fact, a very special feature a very special use of this already appears, for instance, in the thesis of Pablo Guarino. Okay? It's a very, very important step is to think of asymptotically conformal extensions of maps which are real. Okay? So, and by the way, before Pablo, there were already people like Świątek and Grajcik and Duncan Sands that were using these asymptotically conformal maps. Okay? So, but before I get to that, I have to return to the case, to the realm of actual interval maps and introduce some notation. So suppose you have an infinitely renormalizable unimodal map of the interval. The interval I denote by I. From now on, I means the interval minus 1, 1. So as we've seen, if the map is infinitely renormalizable, the nth renormalization can be written like this. Okay? It's just some power of f restricted to some interval determined by this lambda sub n, which is the qnth iterate of the critical point, and it's negative. So in this symmetric interval, you consider this power of f and then you linearly rescale. So these guys, these QNs are just the products of the periods that appear. Okay, so if you were dealing with period doubling, after n steps, you have like 2 to the n. So Qn is like 2 to the n. Okay? Very well. So like I said, these guys are called periods, and the QNs are closest returns. They are closest returns in the dynamical sense, in the sense that in the interval that goes from minus lambda n to lambda n, you don't find any iterates of the critical point earlier than Qn. Okay? All the iterates up to time Qn lie outside this interval. So I denote the interval containing the critical point at that level, delta sub 0 n. And what you have, the picture you have to have in mind is that you have a Cantor set. You know, in the beginning you have, say, let's just look at period doubling situations. So in the beginning you have 2 intervals, one containing the critical point, the other containing the critical value. At the next step, you have 4 intervals. At the next step, you have 8 intervals, and so forth. So the intersection of all these, so you know, take the unions of these intervals at each level and take the intersection. What you get is the post-critical set of the map, which is a Cantor set. Okay? So here's the post-critical set. So these intervals here are called delta sub I sub n. So the ones containing the critical point are called delta sub 0 n. N is the level where you are, and delta sub I n are the images of these guys. Okay? Anyway, so that's just notation, and with this notation, the first fundamental result in the series is Sullivan's real bounds. Ooh, I have very little time, so I have to rush. So rather than you know, going through the pain of, you know, explaining in details the technical statement of the theorem, let me just give you the meaning. So what is the meaning of this theorem by Sullivan? Sullivan found some bounds, universal bounds for this renormalization. So he showed that if a map is infinitely renormalizable, and it has to be at least, let's say, C3, like in the beginning, then the post-critical set, this post-critical set is a Cantor set with bounded geometry. Bounded geometry means that, you know, at each level you have an interval which is subdivided into, which contains some other intervals at the next level. So, and the ratios between the parent and the children are bounded, above and below. Okay? This is what it means to have bounded geometry. So that's one thing that the theorem is saying. The next thing it's saying is that the successive renormalizations of the map are actually bounded in the C2 topology. I wrote here C2 topology right here, see? The renormalizations are bounded in the C2 topology. And moreover, these bounds, which may depend on F in the beginning, asymptotically they are independent of F. Okay? So these are what Sullivan calls bow bounds. Yes? Yes. Everything here is for bounded combinatorial type. Okay? So these bounds are called bow by Sullivan. There is even a little joke. I don't know if I have time for this, but I was there when Sullivan came up with this acronym. So bow means, it's beautiful in English, right? But he used this word because it meant that the bounds were, you know, that the renormalizations were bounded and eventually universally bounded, which is exactly this picture that you have for when you have 4 intervals. Okay? So there's an in-joke there. Anyway, so Sullivan also showed that the limits of renormalization, because now you know that the limits exist in the C0 sense at least, or even in the C1 sense. Right? If the renormalizations are bounded in the C2 topology, then they are precompact in any weaker topology than that, in particular in the C0 sense. So you can extract limits. And what Sullivan showed is that all limits were quadratic-like maps like this, or polynomial-like maps like this. Okay? With good bounds. Good bounds meaning that they are eventually universal. So these are the so-called complex bounds, and the complex bounds are also bow in this sense. They're eventually universal. They're independent of the map. Okay, so now I get to, at least I think I'll be able to get to our stuff. So our let's say our work starts by, let's try to understand if we, you know, what happens if we generalize this notion of quadratic-like map to asymptotically conformal maps. So what is an asymptotically conformal map, first of all? So you have a map which is continuous, defined on some neighborhood in the complex plane, and let's say this neighborhood intersects the real axis somewhere. Then you say that it's asymptotically conformal of order R. R is some given number greater than 1, if it has the following properties. So first of all, it's a CR map in the plane. It is a quasi-regular map. So what is a quasi-regular map? It's just like a quasi-conformal map, except that it may not be invertible. What is a quasi-conformal map? It's a map that infinitesimally maps little circles into ellipses, little ellipses which have bounded eccentricity. Okay? So this is what it means for a map to be quasi-conformal. And quasi-regular is the same thing as quasi-conformal, except that it may be a non-invertible map. It may be like a branch covering or something like that. And moreover, the thing that makes it asymptotically conformal is the fact that these eccentricities of these ellipses, they go to 1 as you go down near and closer and closer to the real axis. So I denote by mu sub f the complex dilatation of the map. It's just the ratio of the d bar derivative with the d derivative. Because I didn't say this, but these maps are all orientation preserving. Because they're orientation preserving, this d bar derivative in absolute value is always smaller than the d derivative, okay? Because the Jacobian of the map is exactly the difference of the squares of the moduli of these two numbers. So mu is always less than 1. And being quasi-regular, quasi-conformal, means that the supremum of the mu's is strictly less than 1, okay? And what I'm saying here is that not only is less than 1, but as you get closer and closer to the real axis, mu is vanishing. It's vanishing with a certain order of magnitude with respect to the distance between the point z and the real axis, which is the imaginary part of z, okay? So this is what it means for a map to be asymptotically conformal, and therefore you can define what is an asymptotically conformal polynomial-like map. It's just a map which is asymptotically conformal in the sense I've just defined, and it also has this geometric feature here. It maps a disk as a branch covering map onto a larger disk, okay? So why are these, and they have to be symmetric and everything, and they have only one critical point and so on. Why are these maps important? Why bother? Well, before I go on, just quickly say that these maps have, they can only be factored. Every such asymptotically conformal polynomial-like map can be written as a composition of a quasi-conformal homeomorphism, a diffeomorphism actually, and a map G which is holomorphic, okay, which is polynomial-like in the usual way. So what is the relevance of these? The relevance is that we have a complex bounds for such maps. So if you start with any CR map, unimodal map on the interval, and you take any extension of it to the complex plane, which is asymptotically conformal. And by the way, these things are if and only if. Every asymptotically conformal map restricted to the real axis, if it's asymptotically conformal of order R, will be CR. And conversely, if you have a CR map on the real line, it admits an extension to a neighborhood of the real line, which will be asymptotically conformal of order R, okay? So if you start with any such map which is restricted to the interval, is infinitely renormalizable of bounded type, then what the theorem says, I'm not going to go through all the details, but it says that you can find pairs of disks containing each one of these intervals at each level, as, provided you go sufficiently deep in the renormalization. You find pairs of disks such that FQN maps the smaller one onto the larger one as an ACPL map, okay? And with good bounds. Good bounds means that the moduli of the annuli of these guys are controlled. And this gives you control on, in the C0 sense and so on. So the moduli are bounded by some constant, from below. The diameter of each one of the little guys is bounded by a constant times the length of the corresponding interval, so that you have also bounds from above on the moduli. So everything is controlled. So this is what the complex bounds are. And moreover, these maps, if you decompose these renormalizations, it has a Stoilov decomposition, like I said before, the distortion, the quasi-conformal distortion of these maps is going to 0 exponentially fast. Okay, because these intervals delta sub 0 n, I didn't tell you this, but it follows from the real bounds that these intervals shrink exponentially fast towards the critical point. Okay, so In other words, ACPL maps appear naturally, okay, as you renormalize. Okay, so let me just, by the way, these complex bounds are not really new. They're a consequence of a more general complex bounds proven by Clark, Van Strien, and Sofia Trejo. And, but here's something new. What we do is we proved also that there are C2 bounds for these maps in the complex plane. These maps are not holomorphic, but we show that the C2 derivatives of these renormalizations are controlled, okay? So this is this theorem. If you start with anything which is ACPL and you take deep renormalizations, these renormalizations are all bounded in the C2 topology, okay? And in fact, the bound becomes eventually universal as well. The proof uses the real bounds I mentioned before, the complex bounds I have just stated, and it also uses this chain rule. So this is why I told you, go home and think about this, because this is what's used. You use this chain rule and induction. Okay? Oh, this is just the tip of the iceberg, of course. So now you see, the idea would be to use this theory of ACPL maps, just like Sullivan, McMullen, and Lyubich and Avila used quadratic-like maps or polynomial-like maps, right? So you have to understand the basic dynamics of these maps. So there are basic questions you can ask about these maps which don't have obvious answers. For instance, are the periodic points dense in the Julia set? Is the Julia set locally connected? What is the classification of the stable components of the interior of the filled-in Julia set? Okay? Can you have wandering domains? I'm going to skip this number 5. I don't have time to explain to you. In fact, I think I overstepped my time already to say what is the pullback argument. Okay? These questions don't have obvious answers. In the holomorphic case, they have obvious answers because there is, it's a basic fact that every polynomial-like map, which is holomorphic, is actually conjugate, topologically, even quasi-conformally conjugate, to an actual polynomial. And polynomials are rational maps. And for rational maps, you have the Julia-Fatou theory, which tells you, for instance, that the periodic points are dense in the Julia set. It also, for rational maps, there is also something called Sullivan's no-wandering domains theorem, which was mentioned by Artur yesterday as well. It tells you that the components of the Fatou set are eventually periodic. There cannot be wandering domains, right? So for these maps, in the holomorphic case, the answers are all kind of obvious. But these maps here, the ACPL maps, are not holomorphic. And they are not uniformly quasi-regular. As you iterate, the distortion becomes worse and worse. So you cannot apply these ideas. You cannot use Montel's theorem. You cannot use any of these tools immediately. However, in the specific case where these maps are asymptotically, they are infinitely renormalizable of bounded type, we can actually answer these questions. And this is the main theorem, and this is the punchline I wanted to get. If you start with something which is asymptotically conformal, or of a certain order R, it has to be strictly greater than 3 for some technical reasons. And you suppose this map is infinitely renormalizable. Then if you look at a deep renormalization of this map, with n sufficiently large, if you call F some deep renormalization, that deeper renormalization will have the property that all periodic points are expanding. The set of periodic points is actually dense in the Julia set. F has no wandering domains. The Julia set is actually equal to the filled-in Julia set. There are no interior components in this case. And the Julia set is actually locally connected. And finally, the map is actually topologically conjugate to, only topologically conjugate, not quasi-conformally conjugate, topologically conjugate to a polynomial-like map. Okay? Of course, once you know this, last item here, you know all of the others, right? But the proof is actually building, okay? So this is the main theorem. So I got to the punchline. I just have to 2 seconds just to tell you what the ingredients are. We use the real bounds, the C2 bounds, the complex bounds, of course. We use the control of the distortion of the hyperbolic metric. So you take this domain V, which is symmetric about the real axis, and you take out the real axis. You get 2 components. Each of these 2 components is a topological disk. In these components, you have a hyperbolic metric, a Poincaré metric. And the proof goes by examining what happens with how F distorts the hyperbolic metric, okay? And then we have to show local connectivity, we have to control the sizes of the so-called puzzle pieces. I don't have time to explain that. And we also use the theory of holomorphic motions, in particular a theorem, a very interesting, very deep theorem called, well, not deep, but very difficult theorem called Slodkowski's theorem. Here are some references for you. This is in preparation. This is already available. The paper by with Sofia Trejo is appearing in Communications. This is the main paper that inspired this whole thing about the CR. Okay, and this paper here is coming from Pablo's thesis, and it has just appeared as well. Okay, if I had time, I would also tell you how the proof goes, but I don't have time, so I'll stop here. Thank you. I'm sorry. Desculpa.